The- Today we are going to study transmission lines and antenna. My syllabus has this transmission line equation, primary, secondary, and then this is the high value section for AE. So I move there next. Like look at the theory. Why do we need transmission line theory? At low frequencies, we can often treat a wire simply as a connection. At low frequencies, the electromagnetic waves are not noticeable. So source to load, but at high frequency, the wire itself has electrical properties. So wire will have electrical properties like resistance, inductance, capacitance, and conductance. These are distributed along the entire length of line. So instead of treating the cable as one resistor or one inductor, we model it as resistor, inductor. This is called distributed parameter model. We model it as resistor, inductor, capacitor, and conductance. Capacitance and conductance. This is called distributed parameter model. The four primary parameters for a transmission line per unit length is R in series resistance and L is series inductance, C shunt capacitance, G shunt conductance. So remember R and G, C are the primary constraints parameters. Why does capacitance exist between the conductors? Imagine a two-wire transmission line. Conductor 1, conductor 2, this is the electric field in the wire. The two, how to explain, why does capacitance exist between two conductors? So this is a question I asked it earlier. In when I'm studying this topic, actually this is a coaxial cable. A coaxial cable has a inside one conductor and outside and one conductor, covered by a metal sheet, dielectric. The two conductors are separated by insulating material called dielectric. That creates capacitance between them. When you know capacitance, what is the capacitor? It has two metal plates separated by an dielectric or air, the open air. Same thing happens here. This is two conductors, two metal plates. In case we have two conductors separated by dielectric, that creates capacitance between them. So the lines behave partly like a capacitor. Why does inductance exist? When current flows to a conductor, it creates a magnetic field around it. When flows to a capacitor, sorry, when current flows to a conductor, it creates a magnetic field around it. That magnetic field stores, therefore the conductor has capacitance. Why does resistance exist? The conductor isn't perfect, it has infinite resistance. V equals to IR, so some energy is dissipated as heat. Why is G is present? The insulation between conductors isn't a perfect insulator. A tiny leakage current can flow to the dielectric. So G means opposite of capacitance, like conductance. We denote it by 1 by R. Right? The insulation between conductors isn't perfect. A tiny leakage current can flow through the dielectric. The leakage is present by shunt conductance G. Primary versus secondary parameters. This distinction is important. Primary parameter. These are physically associated with the line RLGC. Secondary parameters. These are derived from the primary parameters. The two major ones are gamma and propagation constant. Gamma is the propagation constant. Sorry, gamma is not a propagation constant. Yeah, gamma is the propagation constant. And gamma equals to alpha plus j beta, where alpha is an attenuation constant and beta is a phase constant. Yeah, I remember. And j naught z naught is the characteristic impedance. Propagation constant. Here, this impedance is not same as with the impedance you see in AC topics. It is different one. Propagation constant. The propagation constant is gamma equals to root over r plus j omega l into g plus j omega c. It is usually written as gamma equals to alpha jb, where gamma equals to alpha equals to attenuation constant, beta equals to phase constant. It tells us alpha tells us how much the signal amplitude decreases as it travels. Beta it tells us rapidly the phase changes along the line. So gamma equals to alpha plus j beta. Think of alpha as amplitude law and beta as phase change. Characteristic impedance Z naught equals to root over R plus J omega L by G plus J omega L. This is a very important transmission line quantity for an ideal or lossless line. R equals to 0, G equals to 0, so Z naught equals to root over L by C, therefore Z naught equals to root over L by C for a lossless transmission line. Yeah, this is characteristic impedance. You can see we did here multiplication, we did here division, root over of Z naught. This is in multiplication propagation method. Here we divide R by G. This is a very important transmission line quantity for an ideal lossless line. For ideal transmission line, resistance is zero, uh, conductance is zero. So Z naught equals to root over L by C. If we substitute, we get Z naught equals to root over L by C. Therefore, Z naught equals to root over L by C for a lossless transmission. What to remember right now? Don't try memorizing everything at once. Primary RLGC, secondary grammar, Z0, propagation constant, gamma equals to alpha plus j beta. Alpha equals to attenuation, beta equals to phase change, lossless characteristic impedance, Z0 equals to root over L by 3. So here we will look into diagrams, actual diagrams. We will look into the diagrams, transmission and output, same, same, old, P plus J omega P, plus J omega. The key is to understand what is physically in series and what is physically in parallel. Once that is clear, the J omega in J omega is a transmission of. First one correction, the transmission in expression is not J omega C. It is R plus J omega C. For the series path and G plus J omega C for the shunt path. C for series path. First one, the transmission line expression is R plus J omega C. Yeah. I asked why it is J omega L, why not J omega C? I asked. Look at a tiny piece of transmission line. Imagine taking an extremely small length dx. Dx means we do dA by dx of something. It is differentiating. So the differentiating is small part of the transmission line. This is the small part of the transmission line. There are two different parts along the wire series. It contains RDX. It contains RDX, like different very small part of the transmission line's resistance. And it contains an LDX, very small of the transmitter lines in that term. And therefore its total impedance is R plus G omega. So this its total impedance in series, right? R plus J omega. Resistance J omega is the reactance of the impedance of the impedance. Z is impedance, right? This is impedance. Impedance of the resistance is R. Impedance of the inductor is J omega. Between the conductors shunt, it contains GDX and CDX. Between the conductors, between the conductors, uh, it contains GDX and CDX. Therefore, the total impedance is capacitance. It is 1 by J omega C, right? G plus J omega C, that's the fundamental result. Here we give the explanation. Why it gives Bombay geometry, why it gives admittance. But in transmission line equation, a right shunt branch has admittance, not impedance. Admittance is y equals to 1 by z. Therefore, y is equal to j omega c. We get g plus 1 by j omega g. G plus c omega c. I is g also the shunt branch. Conductance G prevents leakage through the insulating material between the conductors. So, these are two conductors. We got between them is an capacitance and conductance. Both C and G connect between the two conductors, so they are parallel. Parallel elements are naturally represented using admittance. Phi equals to G plus G omega C. Because inductance is not physically a shunt element, in the standard transmission and model, magnetic field associated with current along the conductor is represented by the series inductance. Similarly, electric field energy between conductors, capacitance, heat shunt, magnetic field energy around conductors, inductance as series. The easiest way to remember, think of the transmission like series, like this series resistor of inductor. This is shunt. The reason why he is saying series means across the transmission line, we know resistance, we know inductance. Resistance happens naturally, inductance happens naturally at a particular part. But the shunt means where the coaxial cable, the transmission line has inside one conductor, outside one conductor. This creates a capacitance and conductance between them. So we rather instead of impedance, we rather use the admittance. So both are in parallel, we use admittance. So that's why G plus G omega C. We go deep, what the meaning of series in transmission line. What the meaning of the transmission induction are normal DC circuit of AC. We know what series means. But for coaxial, it's a special type of circuit. How do we just object? Will answer. Exactly, series and shunt don't mean something different just because it's coaxial. They refer to where the distributed electric effects exist alone. The important part is the transmission is not a single component, it's resistance, inductance, capacitance, recurse that are continuously along with it. Think about the coaxial cable. Look at this. Inner conductor, dielectric, outer conductor. There are two conductors, inner conductor, outer conductor, shield, the signal travels along the cable. What does the series mean? Direction of the signals, any section. So, direction of the signal. The current flowing along the inner conductor. Inside the inner conductor, a tiny resistance will be there, a tiny inductance will be there. So, from the perspective of a signal traveling down the cable, these are in series with the signal path input, RDS, LDS output. That's what series means here. It doesn't mean there is a physical resistor and inductor sitting inside the coil. They are model of the electrical behavior of the tiny length of the cable. What does shunt mean now? Look between the inner and outer conductors. The dielectric separating them has capacitance, a tiny amount of leakage, so we model that tiny section as inner conductor, outer conductor. So between the two conductors, there is a dielectric material separating them. So we say capacitance is there, a tiny amount of leakage is there. So we model the tiny section as C and D in series, parallel with the inner and outer conductor. So this is across the signal path. Uh, so it is called shunt. Remember shunt connected across the two conductors. Put both together. So if we put both together, where this is inner conductors, resistance and inductor. This is between inner conductor and outer conductor. There is a capacitance and shunt, resistor shunt. The bottom line represents the return and outer conductor. Along the cable, it these two are parallel. Between the conductors, these two are parallel. Why is it called distributed? In an ordinary circuit, you might have RLC, but in a transmission line, the effects are spread continuously. So this is the distributed part. In a normal, these are physical components like resistor. We had a resistor, but the ideal transmission line, the transmission line itself has high frequency electromagnetic waves. So every small part of the wire is important. A wire itself has some resistance in capacitance and by default in a coaxial cable. So this is for every tiny dx of the coaxial cable. Everything has a resistance in inductance in series and shunt like that. There are effectively infinitely many tiny sections. That's why we call RLGC distributed parameters. So coax isn't a special type of circuit. In this sense, you still apply normal circuit concept. The difference is normal lumpy circuit. You say R equals to 10. Put one resistor somewhere. Transmission line say we say R equals to R dash, L equals to R dash. Because it's changing. Because these properties exist along every meter of the cable. Uh, the best mental picture, don't think a coaxial cable contains one resistor. So it's not changing. I mean, R equals to R dash what we meant with. Like so many resistance are there for tiny diagram. Every tiny piece of behaves like RL size path and tiny GC funds path. Then thousands, millions of these tiny sections together form the actual transmission line. That's why the transmission line equations contain R plus J omega L and G plus J omega C has proof. If you say then why propagation constant gamma is root over multiplication of series and shunt equation. Y in impedance is division of series and shunt. Exactly, this is the point where the formulas start making sense instead of looking like something to memorize. Let's call the two distributed quantities Z naught equals to R plus J omega L. This is series impedance per unit length, and Y dash equals to admittance. This is admittance, that is the impedance. G plus J omega C. This is shunt admittance per unit length. Now we can understand both formulas. Why does population constants use multiplication? The population constant is gamma equals to root over impedance into admittance. Series impedance into shunt admittance. Or root over y multiplication, because gamma describes how the signal changes as it travels along the line. Remember that the line has both series effects, signal losses, changes everything energy while traveling shunt effects from energy stored leak or across the conductors. Both effects act together. So the amount of change during propagation depends on the interaction between series impedance and shunt admittance. If we give the gamma square equals to series impedance equals to shunt admittance, and therefore gamma equals root over series impedance into shunt admittance. We can think it as propagation requires both the along the line effect and across the line effect. This is along the line effect means series impedance. This is across the line means shunt admittance. Why does characteristic impedance is division? The characteristic impedance is Y division because Z not tells us the voltage or current ratio exists for a wave traveling along a. This is true, right? Z not tells us voltage and current ratio V by R equals to V by or AC Z equals to R equals to V by. So for a wave traveling along the infinite long or properly line terminated line by definition we say Z not equals to V by. Voltage is related to the series impedance which while current is related to the shunt dimensions. So here voltage means uh, capacitance. Voltage means how voltage is related to the series impedance, while current is related to the shunt dimensions. So the ratio naturally appears Z not so refers to Z. The Z dash by Y dash giving Z not equals to root over Z dash by Y dash. So we get this by that way. Here we can ask another question. How you set voltage uh, refers to series uh, impedance and how you say current refers to shunt admittance. Uh, Take a tiny section dx, series impedance zdx, and we have y dx as shunt admittance, where z dash equals to r plus j omega L. Y dash equals G plus J. What does the series impedance do? The current I flows along the line because there is series impedance Z dash df. There is a voltage drop. Yes. In series, like there is a resistor, there is a voltage is dropping. So dV equals to minus I Z dash dx. So dV by dx equals to minus Z I. This is series impedance connects voltage change to current. What does shunt admittance? The shunt branch is connected across two conductors. The voltage across it is V using I equals to YV. The small shunt current is equals to Di equals to minus V by D dash dx. Therefore, Di by dx equals to minus Y dash V. So the shunt admittance connects current to change to voltage. Now the two equations, these two equations starts the final input. If it's same for so for propagation constant also, we say z dash equals to y dash because um, series impedance refers to voltage and series shunt admittance refers to current. And this also explains why z naught equals to v by 2 to z dash by y dash. Z dash causes voltage drop according to I, y dash causes current change according to V. And because these two effects are coupled, we get gamma equals to root over z dash y dash, while the ratio gives Z naught equals to impedance equals to root over z dash by y dash. Okay, we'll stop here. We'll continue later.